Oh, no worries. Thanks for the heads up. I'll call on you a lot then. If I'm reading that right, you're basically saying, please call on me constantly and give me really difficult questions, and I'm on it. Count on me. So the point of this being, this is one of those areas where high chance of getting passage, and if not a passage, definitely some freestanding questions. And so I want to start with just basic notion of reflection. So when light strikes an interface, light is like any other wave. When it strikes an interface, potential for a couple things to happen. Number one, it can penetrate into the new medium known as refraction, where it passes from one medium to another. When you change medium, you change speed. So depending on the angle at which you enter at, you can get a change of the propagation angle for the ray. But also at that interface, you can get absorption and reflection. And so I'm going to worry about those three things: refraction, where it passes into the new medium; reflection, where it returns or actually never leaves but stays within the same medium; and then absorption, where that interface absorbs some of the light as it penetrates through. Okay, so with that in mind, one of the first take basic note or basic look at reflection. If light comes in, and the single ray is going to represent one photon within, I guess, a series of photons traveling in that same direction. But if the ray comes in, strikes here, reflects out, what is true of the angle in at the angle out? So how do the angle in and angle out compare to one another? Equal. Yep. Just like throwing a ball, just like a ball rebounding off a wall, or recoiling, or whatever you want to call it. There's angle conservation, for lack of a better term. So I'm going to put the angle here because that seems like the logical thing to do. But is that the angle they actually use, or do they use a different angle? Unfortunately, because of Snell, they could have easily done that. Angle with respect to the surface, but that's not the way they actually do it, unfortunately. So rather than making life simple, Snell decided to make it based on a perpendicular line. So a perpendicular to a surface is known as a normal. Hence, that's where we get the term normal force, the force perpendicular to a surface. The incident angle is with respect to the ray and the normal to the surface, reflected, normal, on the ray. Still, angle in equals angle out. So for instance, if that was 30 and that was 30, that would make that one 60 and that one 60. So the same notion of what we're saying before, but just we want to stay within their convention. So the incident angle is the angle between the incident ray and a perpendicular line to the surface, starting from where it intersects. Okay, there's a concept known as thin film interference. So I want to do a little background on that, because that ends up being, for whatever reason, a cool little question to throw in here and there on the MCAT. So the concept of phase shifting. So let's consider these two scenarios. This wave is coming in, so it's up, it's down, it's up and down. So I showed two wavelengths within that wave, same thing here. When it strikes the surface and reflects back, we decide based on value what it's going to do. So what is the n value? Pretty important concept to know. It's known as the index of refraction. The thickness of the medium is what we're going to study, but that's not n. N is a speed phenomenon. So what is the fastest light can go? What medium? Solid, liquid, gas, vacuum? Where's light the fastest? In a vacuum. So what the n value is it's what I'd have to multiply the speed by within a medium to make it equal to the vacuum speed. So in other words, the speed of light in a vacuum equals n be within that medium. So for lack of a better term, it's called the index of refraction, but if it's okay with you, I'm going to call it the slowness correction term. The slower it is, so if it goes into a solid, it slows down a lot and is very big. If it goes into a gas isn't very dense, so speed doesn't slow down very much. So therefore n is tiny, like 1.0 something for a gas. But n is the slowness correction term. So n is c over v. which basically means is n ever less than 1? No. Speed of light in a vacuum is the fastest it could possibly be, so the numerator is always going to be bigger than the denominator. So n always has to be bigger than 1, except if it is a vacuum. Okay, so here's what happens. If you're in, let's say, air and hitting plastic, so something with an n value of around 1, and you're hitting a solid, let's say n of 1.5, are you going from a lower number to higher number or higher to lower? Hopefully it's a straightforward question. Or from 1 to 1.5, low to high. I want you to remember this phrase, low off of high, pi, and then 1.4, let's say it's in a liquid, and it hits, let's say, some oily plastic, some gelatin, might be higher to lower, so 1.4 to 1.3. Is that going from high to low or low to high? High to low. Okay, I hope these are freebies. So low to high, high to low. The reason I'm pushing this on you is for the following phrase. Low to high, pi. So it goes from a low and reflects off a high, low off of a high, or low to high, pi. High off of low or high to low, no. What does that mean? So what it means is the following. Oh, it still reflects, but it reflects with what's known as a phase shift. So what pi means, how many pi's is it to go around a circle? How many to traverse an entire circumference of a circle is 2 pi? Perfect. So going around a circle is also known as 360 degrees. So oftentimes I'll refer to this as a 180 degree phase shift. So notice how the wave is going up and then down and up and then down. It should have kept on going up and then down, up and then down. But instead of going up, it's doing the exact opposite. It's going down, which means it's at 180 out of phase. Would I have to move this 1/2 of a cycle, 180 degrees, to get it lined up again? So if I was just following this wave, up, down, up, down, down, up, down, up, I did the complete inverse. I did a pi shift. Okay, whereas on this one, notice up, down, up, down, up, down, up, down, did the same thing. So low to high, pi, it shifted, high to low, no. Here's what that means. So if I take this wave, so this first part right here is that incident. So this is going to be the exiting wave. This first part is there, this exiting one. So this will move up and end up there. This one's going to go and end up there. So what this means is the wave went in up, down, but reflected down, up. It was completely inverted. I don't know, good question. Does the difference matter? So does it really make a difference? Well, tell me about constructive and destructive interference. So if I added these two waves, they're both up, oops, sorry, up, down, up, down. So what kind of interference would I get? Oh, the amount doesn't matter. Yeah, the amount of like difference, if it's barely different or substantially different, you're still going to get the same shifting. Okay. What about if I added, I don't know if this one, I'm trying to draw it better. So here I have up and down and up and down and up and down. So what do you get for that one? Destructive. So what happens then is, and I'm going to go to the next picture to do it, but for now, just hopefully this is reasonable for you. You can remember low to high pi, high to low no. Low, light coming from a low and reflecting off a high, pi shift. Light come from a higher end to lower, or reflecting off a lower end, high off of low, no. So just remember, low to high pi, high to low, no. So if we do that, here's where this kicks in. This is where the application is. If I want to measure how thick a coating is, let's say I put a protective plastic coating on something. such as, I don't know, an endoscope. So what is an endoscope? Probably should know what this is because it's going to pop up a couple times today. Endoscope, basically a camera with a long fiber optic cable attached to it that you start pushing into a body through whatever orifice you decide to enter in through. So could go down your throat, could go through other portals as well. It's just something they put into your body. Okay. I don't know if it goes in through the belly button. If you do that one, you probably will lose your medical license. Just saying. If you have to drill to get the camera in, you're probably, yeah, I guess, and I take it back. Like arthroscopic surgery, the scope part of that is doing that. But yeah, it's basically, if you're looking at the digestive tract, upper or lower end of it. So yeah, definitely. That if you're trying to look for the alien baby, that is true. You would do that. Okay, but we put a little plastic coating on the can because we don't want it to interact with the body. We want to keep it, hygienic and also not to get scratched up, gummed up, chewed up, whatever would happen with the body. So we don't have a protective layer we peel off, but we want to know how thick that layer is to see how it interacts with light. So here's how I can measure the thickness. I'm going to do the same thing as before. I'm going to send a light ray in. And so it's going to go in. Some of the light's going to reflect off the upper surface. Some is going to refract in and then reflect off the lower surface and come out that way. And so at the upper interface, we're starting 1.3, the medium is 1.6. 1.3 to 1.6, is that a high low or low to high? Low to high. So this one's going to get shifted. This upper reflected ray is shifted. Nothing happens when it refracts. It's just going to go through. But on the lower level is a lower reflection, high to low or low to high. So 1.6 compared to 1.3, high to low. So is the lower one going to be phase shifted? Yeah, low to high pi, high to low no. So the upper one gets shifted, the lower one doesn't get shifted. So if that ray starts out in phase, what's true? Ah, perfect, comes out of phase. One is shifted, the other one isn't. So let's say two rays came in that were coherent in phase. Now they're out of phase, which means you will or won't see whatever color that is. You will not, it'll cancel itself. So here's my food for thought. Is it important that the thickness of this is exactly equal to half a wavelength? So let me go ahead and send the ray in. So here's our wave coming in. So down, up, down, up, down, up. When it hits here, it's going to travel in. If it just so happens that the thickness of this film corresponds to that wave right there. So let's say, for instance, I'm using green light. And let's say I get lucky and green light, half a lambda of green light happens to be the exact thickness of that film. And it's going to be half a lambda there. And again, off this, high to low no. So it's going to keep on going the same way. So it's going to go out like that. And then it's going to just keep propagating the same way when it exits. Whereas this one's low to high pi. So this one is going to, if it's up, down, it's going to be up, down. So this one got shifted, this one didn't. But just because it happened to be the exact thickness of this wave right here, half a wavelength, does that mean this color is not going to be seen? So it's kind of cool and weird thought, but does the angle matter? If I went at a different angle, would I be traversing a different distance and would it be potentially a different color? So you agree, let's say it was closer to vertical, you agree it'd be a little bit shorter, a little bit more of an angle. Yep, it's a phase shift, you won't see that color. So have you ever seen a soap bubble? This is the one they always like to point out. So a soap bubble is a very thin film that has air, material, and air. And if you ever looked at a rainbow or looked at a soap bubble, can you see this weird sort of rainbow on it? And how many have ever noticed that sort of rainbow or that little prismatic color? That's what you're seeing. It's not that you're seeing a rainbow, you're seeing the absence. So at one angle, green might be removed, which means it looks red. Another angle, blue might be removed, which means it looks orange. Another angle, purple might be removed, so therefore it looks yellow. And so because every single angle is a slightly different length, yeah, exactly. That's why the angle does matter. So you just asked about the angle, exactly. So if the angle is flatter, it goes in, the longer the distance, closer is the vertical, shorter the distance. And so if you're looking at a soap bubble, you agree, you might be looking, let's say right here, there's you looking at it. This one's gonna be straight on, that's gonna be different, that's gonna be different. So because these angles are all slightly different, this one might be missing blue, this one might be missing green, might be missing yellow and so forth. And so looking there might look one color, then here are different colors. So you start seeing a little rainbow effect on there. Okay, so how is this useful to me? From a physics standpoint, the whole purpose of this experiment, if there's only one color that the right angle, the correct angle, will make disappear, then if green disappears, so if I shine green light on it at a certain angle, and then I go to a certain angle and green disappears, if I know the angle coming in, I know the angle, I know the thickness of it, can I measure how thick this is based on the color that disappears? So there's only one color that will be the exact right wavelength that'll match perfectly with that thickness. So is it a tool for measuring the thickness of very thin films? Yeah, basically it's trial and error with the angle. So if you ever seen the device, they crank it at different angles. When they get the correct angle, then they'll know. So you lock onto a wavelength and you figure out the angle and you can work that way. But yeah, it is trial and error, because if you knew the thickness of the film, then you could pick the right color. Because you don't, you have to go ahead and pick a color and adjust the angle. But it's kind of cool if you think about it that way. So it is, I think it's kind of a neat system. But an application that maybe could show up on your test, years ago, and talked about this real briefly in a previous lecture, so I want to reintroduce this, but when they do transplants, when they put, let's say, an artificial hip, a screw, anything in your body, is it important that they make it, or I guess not oxidation proof, but is it important that they do something to minimize the damage caused by oxidation? So what they'll do is they'll put a thin coating of oxide on the outside and then the actual core material on the inside. And so if they want to measure how thick that oxide coating is, they don't want to get it too thick, they use thin film interference to measure the thickness of that. That might have been something that the MCAT test writers once upon a time were interested in asking students about. So just kind of cool how this thing works. So first question of the day, 3, 2, 1, and I swear you're up. So see how this one goes, give you about 40 seconds. Hey, sorry, logistic question. I apologize for this, but I got a text from Patricio that somebody from class wasn't able to get in. They didn't have the link. whoever that was, are you here now, or is there somebody still jonesing and try to get in? Just seems like the list of everybody here are names of everybody who's normally here. So I think, yeah. And I think it's, oh, okay, perfect. Then it all worked out. All right. Okay, so for this one, incident light shining on the film shown below. So that gray material represents the film. Oh, so sorry. And that's a good question because unfortunately, because I'm in class, I can't actually log into it. But is it still on the portal page, or is it on the Discord page? I think everything is on the Discord page you guys made, which thanks again for just, being the real portal. But I think that's the go-to for all those. Sadly, that's actually how I find things now too. Okay, so the thin film is here, goes from air, hits the material, goes through. So I'm gonna have reflection off the air material side, and then also the air liquid B side. And so it's the right thickness to lose yellow light. So if it were thicker, if this material got thicker, what would be true? So let's say it's a certain thickness where these two cancel one another. If it's thicker, then what's true? To be thicker would take a longer, shorter wavelength. Longer. So the thicker it is, the longer the wavelength you would need to be just perfect to be out of phase. So if yellow is when it's narrow, if it gets wider, it has to be a longer wavelength. Is an orange light, orange photon higher or lower, longer, shorter wavelength than yellow? Yeah, I can't remember. So fortunately, I know Roy G. Biv. I know ultraviolet is dangerous, so short lambda high energy. I know IR, not so bad. I don't wear sunscreen for that, so that's long lambda low energy. So based on that, I know if I go from yellow to red, I'm getting longer. If I go yellow to violet, I'm getting shorter. So yellow to orange is a longer wavelength. So if orange is longer, then that might be true. If it gets thicker, instead of yellow being the right wavelength, it might be orange or red that's the right wavelength. So statement A, true or false? Statement A is true. Perfect. I'm going to erase what I have here. Erasing it in 3, 2, 1. So that one's out. The N for air is less than the N for material 1. Is that just straight memorization? So gases, speed of a light in a gas is just about what it is in a vacuum. So N is minuscule, you don't have to correct it very much. But N in a liquid or a solid, light slows down more. So you have to correct it by more. So N for a liquid or N for a solid is a bigger number. So B is true. B is just background information. C, a phase shift occurs when light strikes a material with a smaller N. Is that one of the things you now have memorized? So is that low to high or high to low? No question mark allowed, dang it. High to low, no. You went from a higher one to a lower one. High to low, no. That's my false statement. And then finally, if air replaced liquid B, the same result be observed? I assume, but I don't know 100% for sure. So I'm gonna give it a small t rather than a big T or a question mark, but I'm happy. C is my best answer. So I'm feeling pretty good about this. So mathematically, highly unlikely you'd ever have to do anything with this, but conceptually you need to know the impact of longer and shorter and just have good intuition. So how many feel like you kind of get it? And you have low to high pi, high to low no memorized? So perfect. High to low no, low to high pi. And then you can kind of visualize it. If you can do those two things, you'll be set on any questions they throw. And just know that thin film interference is used to measure the thickness of a thin film based on the color that disappears, based on the color that's destructively interfered. Okay. Second major topic, total internal reflection. So again, repeat to me, I've already forgotten. What are the things that can happen to light when it goes from one medium and strikes an interface between another medium? It could be reflected. It could be refracted. And it could be absorbed. So here's my goal. So I'll tell you what my goal is, and then we'll talk about how we're going to do it. I want to send light from one end way over here to miles and miles away over here. I choose light because it's very fast. So if I send light down this pipe, let's say it hits here, is that good or bad for getting what I want? Dang it, so bad. I don't want to lose light. And then do I want the material to actually start absorbing some of the blue light? So I'll absorb a little bit here, a little bit here, a little bit here, a little bit here. So do I want absorption? No. Do I want refraction? No. The only thing I want to have happen in this pipe is reflection. I want total internal reflection. I want to reflect it back inside, reflect it back in. So that pulse will go and shoot down and get to the other end. Why would that be helpful? Why would being able to send a light pulse without any refraction or any absorption help me? How would it make the world a better place? Light is fast or slow? Oh, it is partly absorption. So what we're saying is there's three things that can happen. Reflection, that's good. Refraction, losing it on the outside, bad. Absorption, losing on the inside, bad. So if I lose a little bit here and here to molecules hitting it and absorbing it, it's going to go from high intensity to lower intensity. Oh, yeah. Let me do that real quick then. Can you pass co-host to somebody? I just did, so that's okay. I think it should be good by now. But yeah, I was able to do it. Okay, so again, my goal, I want to get transmission down here, send the signal for two reasons. Number one, light sends it very fast or very slow. Sends it very fast. Number two, light can be translated. Because we have machines that can absorb it, translate the information, so it can be coded. You can send a message specifically. So for very fast transmission of information, picture a digitized packet of information, whatever it is, this is great if we can get rid of refraction and get rid of absorption. So here's how we're going to do it. So first, one critical angle. So erasing this in 3, 2, 1. Sorry, I did it a little sooner. I want to start with this. If you've ever been standing in really pristine water, can you see fish swimming around your feet? And how many have ever seen that? Fish swimming around, you can see them dart in and out of your feet. Okay. If you watch the fish, you can see them below your feet, but as they start to swim away, does there come a point where suddenly they just seem to disappear and the water just looks dark? And it happens fairly quickly. So the cone of visibility, you're standing here. And the water's up to, let's say, here. Your cone of visibility is about here to here. Any fish within here, you can see it, but once they go on here, they seem to disappear. The water is very clear and pristine. Here it's dark. Can't see much. Because what has happened is any light inside the water, when it comes up here, reflects in. It doesn't escape. Water here can get your eye. Water here can get your eye. But water beyond that can't get out. So it's essentially this cone of visibility. And reality is I should be doing that with a light and making this dashed. So okay, so let's figure out why that happens. So here's what we're going to have. So I'm going to erase my picture, artistic and beautiful as it may be, and say, let's say you're looking at some fish. So I have some fish here. The light will come off the fish. When it goes from water to air, is it going from high to low or low to high? Slower to faster or faster to slower? And this becomes somewhat important. Going from a high end to a low end. It's faster in water or slower in water than air? Okay, so it's going from slower to faster. I want to introduce Snell's law just for a moment, but n1 sine theta 1, if you recall, equals n2 sine theta 2. Let me make that 2 a little more like a 2 unless I can equal sign. So how many have definitely seen Snell's law at some point? Okay, so I'm going to say n1 is water, so this is slower. So that's a big N because it's slower, which means the angle must be smaller. So hopefully that seems okay. So if you're going from a slower to a faster medium, the angle here has to be smaller than the angle here, meaning does the ray bend toward or away from the normal? You go from a slower medium to a faster medium or away from the normal. This is something also worth memorizing. So I need to memorize phrases, not actions. I want you to say low to high pi, high to low no, for the phase shift associated with reflected light, but then for transmitted light, refracted light, light that passes into the new medium, when you go from slower to faster, you bend away from the normal. So slower light, or light traveling from a slower medium to a faster medium, bends away from the normal. Okay, so know that. That's like one of those things that you'll be able to apply to tons of situations when it comes to refraction. Okay, going to erase what I have up here. 3, 2, 1, clearing. And so here's what I want to note then. Light comes in, it bends away from the normal, but still it can reach my eye. So that fish right there, I can see it. If that fish had a friend, somebody else in school, maybe somewhere over here, it's going to go up. So it's getting a little bit further away. The angle is a little bit bigger coming in, so it's a little bit bigger coming out. If I look at a fish a little bit further over still, I can barely see that one. But is this fish up here the one that's now gone? Is this the one where the angle comes in and it doesn't escape? The refracted angle is 90. So what do they call this angle right here? The one where the angle is 90? The word's on there for you to see. This is known as a critical angle. It's the angle where light can no longer pass in the new medium. So when you're at or beyond the critical angle, light doesn't refract. You don't see it pass through. So the fish here, that light's just going to reflect back in. You can't see it. So you can see all the fish up to that point. Then that one is just gone. You don't see that light coming out anymore. Okay, so the critical angle is the largest angle, or well, I'm going to define it differently. It's the angle at which you get 90-degree refracted. Okay, so with that in mind, I'm going to say, using Snell's law, shoot, aren't I missing sine of 90? Doesn't that go in there or no? Perfect, it's gone. So the critical angle depends only on the two n values. So if I did my math, I'd say that n air divided by n water, the smaller n divided by the bigger n equals the sine theta of the critical. Okay, so I'm gonna come back to this. That's gonna make, I'm gonna pick on this a little bit later, but Snell's law, n1 sine theta 1 equals n2 sine theta 2. Sine of 90 is 1, so we ignore it. So n1 equals n2 sine theta critical. Okay, feeling good about this. So here's how we're gonna apply it to fiber optic cable. Try to combine these two notions and have you help me out. So I'm gonna send light from this city to this city through a cable. The cable is gonna be slant. It'd be nice if it was straight, but it doesn't have to be because it's not a straight path from point A to point B sometimes. So I'm gonna send a photon in. Here's my photon coming in. What is this dashed line again? I've totally forgotten. The normal, perfect. So here it's going from a big angle to a smaller angle. So this is going from faster to slower. So whatever medium I'm starting in, I transfer it into this cable, and now it's bending towards normal. So this must have a large or small n, the cable. The angle got smaller, so n must be bigger, exactly. So the cable has a bigger n, bends towards it. So everything's fine, light's gonna go here, but now I have my decision to make. So I'm gonna draw my normal right there, and then I need a critical angle. So I'm just gonna say, let's say the critical angle's around this. Let's say it's around 45. I'm just arbitrarily putting one. Is this light beyond, at, or within the critical angle? So if there's my critical angle, this incident ray is beyond it, at it, or inside of it. I know, here's my critical angle, that line right there. That line right there represents my critical angle. Maybe I'll do it in red to emphasize it, but that line right there is the critical angle right there. It's beyond it. This is beyond it. So I forget, can you see the fish that are below your feet or the ones that are beyond that cone? From your own personal experience? You can see the ones here at your feet. You can't see the ones beyond it. So does this light escape so I can see it or no? Nope. It's beyond the critical angle. So I get total internal reflection, meaning no refraction. So the ray reflects off and it hits here. I have to do the same thing again. There's my normal. There's my critical angle. The ray is beyond it. Once again, because it's beyond it, no refraction. So once again, flex, hits here. Same thing, have this. There's my critical angle. It's beyond it. So it goes through until finally, now, because I'm going from a more dense to less dense medium, so it's can actually, well, my incident angles, big incident angles, getting bigger, so I'm bending away from normal, so I must be going slower to faster, but it can go ahead and escape out this way. So can I send light from here to here as long as every time it hits a wall, it's beyond the critical angle? Okay, let me redraw it somewhere else. Here's an angle. Is this inside or outside? Let's just call this the angle. Let's just call this inside. Is this in it or beyond it? Outside, perfect. So let's take that same coloring. Here's inside the angle, and here's my ray. So the ray is inside the spot that it could possibly escape or beyond the area where it can escape. Okay, perfect. So it's basically what we're getting at. So inside, outside. So outside of it, same thing, outside of it. So it's said to be beyond. Oh, this is, it's one of those things that when you see it, you get it, but until you see it, this is a butt kicker. This is one of the harder things I had to study for physics. At least this one was painful. Until, honestly, thinking about fish swim around my feet was the only way I ever understood this. So it's only in that vision field where I can see it, because light escapes to my eyes. Anything beyond that, I can't see. So I apologize, I keep on doing that analogy over and over, but that's the only way I ever learned it. Okay, Again, I do this because I want light to be passed through this. So tell me a couple properties you want to have true. Number one, do you want very large or small critical angles? Which would be better? The smaller the critical angle, the better, because then you have a greater chance of being beyond the critical angle. And you want the light to pass through it or be absorbed by it. You want light to pass through. What's really interesting, have you ever noticed plastics have a really faint yellow color? A lot of polymers that they use have, like, whatever the impurity is, whether it's a nitrate impurity, whatever's in there, has a very slight yellow color to it. What is the complementary color of yellow? Purple. Perfect. So because it's purple being absorbed, it looks yellow. So what happens is if you try to send white light through a cable, blue light might get through okay, red light, yellow light, everything, but purple light gets absorbed. So whatever image you get down here, you lose some of the purple. Really cool thing, but if you watch a live event, and how many have ever seen like a purple team? Like if you watch the Kings basketball team, Lakers basketball team, TCU football team, there's certain schools that are purple in color. When you watch these events, anybody notice their uniforms look a lot bluer? I'll get to that question in a second. I kind of want to stick to the one. I'm trying to avoid dodging around. So I see it and I'll get to it in just a second. But in exchange, how many have ever noticed that Barney isn't as like Barney Unplugged, where he tells off-color jokes and sings raunchy songs? Or if you watch a sporting event with a team that wears purple, anybody ever noticed that they end up looking more blue? Is this something anybody has ever even noticed when you watch a team that is purple in color, but they end up blue on the screen? Okay, that'll be your homework to figure that out. Okay, and the other thing, why do we want an angle to be small again? So I do or I don't want the ray to be, I want the ray to be inside of it or outside of it for this device to be effective. My goal, I want to get light from here to here. So I do or do not want to lose light out of the side. I want it to be outside exactly, because if it's inside, I lose the light if it's beyond it. So if this is really large, then I lose it. But if it's really small, I don't lose it. So you want this angle to be large or small? Yeah, kind of the same thing. So as the critical angle gets bigger and bigger, there's a greater chance of being within it as opposed to being outside of it. So I'll end up losing light that way. But as this angle gets smaller and smaller, there's less and less chance for the ray to be in it. So if there's a spot where if you step, like, I don't know, super glue and it's really smelly and you're gonna be stuck there, would you want that spot to be really large on the floor or really tiny? And on some walking pathway. That's a really weird example, but yeah, it works. I mean, it's just the smaller it is, how much you can see the fish. That's kind of what it is, the region where you can see it, because light can escape. And again, I just am such a firm believer is in, if you can understand a real life example or an analogy, you understand it so much better than just trying to, I don't know, think physics, at least for me. Okay, the questions you're asking, I've also been blowing it off because, oops, sorry, let me erase everything here. So again, small n over big N, sine theta critical. And then that equation will pop up in a second. But here's that exact same question, but I want you to answer it now. So I'll give you about 30 seconds and then we'll talk it through. Okay, so again, we want light to pass through. So we do not want, so the fiber optic cable we want, for a fiber optic cable, we want 1, no absorption, and 2, no refraction. I apologize that my spacing is bad here. So which one is going to have no absorption? A cable that's opaque or transparent? Transparent. So in order to achieve this, I want it transparent. Number 2, we want a very small wedge or large wedge that light can escape from. We want a narrow wedge. That. So we want a very small n value. So hopefully that seems okay. So light must pass through, it must be transparent. And then here again is that same thing. So here is my ray coming in. And let's say the critical angle is up here. Would you agree that's a really large angle? Which means it's going to be able to escape easily. But if we make this angle much smaller, now do you agree it's much harder to escape? What does transparent mean? So okay, let me ask you this. You want your house to be bright. You want all the light from outside to get inside your house. You want your house to be totally bright. You don't want to turn on any lights on. You want your windows to be clear or murky and cloudy. You want your house to be as bright as possible. You want to be clear. Clear means transparent, light gets through. Opaque means cloudy, doesn't allow light to pass through. So you want light to pass, you want it to be transparent, no absorption. So is it more word choice than anything else? Because when I said the word clear, suddenly did it make all the sense in the world? When I say clear versus cloudy, clear versus murky, it makes total sense. When I say transparent as opposed to opaque. And how many suffer that same plight? When you change words out of my comfort zone, that's where I started getting into trouble. Well, okay, it comes back to that same idea. You want light to get into your house, don't you? Okay, so you want the windows to be clear. You don't want them to absorb light. You want them to let light pass through. The cable, you also want to let light to pass through from outside to inside, from way down the road to inside your house. So you want the cable to also be clear, not cloudy. You want light to get through it. You want the cables to be clear as can be so light can pass through them. You don't want them to be murky or cloudy or opaque to not let light through. So light, fiber optic cable, light has to get through, so you don't want it to be absorbed and you don't want it to be refracted away. Oh, you're welcome. Okay, so this concept, the small angle still kicking in. The key thing here, back to the equation, sine theta critical, n air over n cable. So if I want the smallest possible wedge, I want this angle to be small. So I want a small angle. N air is what it is, so I want n of the cable to be very large. So I want a very large n value, and I just totally butchered this question. Can't believe I... Yeah, that's where yeah. Yeah, I basically butchered my own question. Kind of embarrassing. But yeah, I went the small possible angle. Angle is smaller as n gets bigger. So Sorry for my circling things off. So, whew. Would you believe that I was a TGL, or was that a Todd screwed up? That's a TGL. I'm going to blame it on that, but hopefully that seems okay. So large N, small angle, transparent, so it's clear and get things through. I definitely have a new favorite student, the person who said, yes, it was a TGL moment. So thank you, favorite student. Okay, third thing to cover then. So hopefully fiber optic cables tend to show up. That whole concept of thin film interference and measuring thickness, nice freestanding question every now and then. One of the things that is highly tested, mirrors and lenses. So this is one of those where I'm going to treat this differently than I assume any way you've ever done it before. Sorry, got one of these cool desks that's supposed to go to different heights, and it's all freaked out. So sorry if you hear me making all noise and wrestling with it. Okay, so what does a mirror do? Does a mirror reflect or refract? Mirrors reflect. So if it comes in straight, it goes out straight. If it comes in an angle, reflects in an angle. Okay, so for whatever reason, can't tell you why, but somewhere along the line, physics people decided the only two things that apparently cause reflections are arrows and candles. So how many had a professor that gave you arrows? Always put an arrow as the example of something they're reflecting. Yep. And if you had really advanced, maybe a candle. Oh my gosh, you had the really high-end textbook with trees. But yeah, simple picture of a tree. And it's just so we can pick a position on it. So hopefully this seems okay. So we have reflection. So light will come in. So I'm going to trace an arrow out. It's going to hit the mirror. Going to trace an arrow out, hit the mirror. And when this happens, we'll see, goes out, reflects back, goes in, reflects straight back, goes here, reflects straight back. Okay, as opposed to a lens. Does a lens reflect or refract light? So lens reflects or refracts? It refracts. So light passes through a lens. Refraction is where you pass through. Reflection is where you bounce off. So it passes through. I actually want you to, why not both? It's just what happens. So the nature of the material, for whatever reason, some are transparent, they let light pass through, some are reflective, won't allow light to penetrate and reflects off. Okay, so what I want to do is I want to take your left hand, put your palm down here, curl your hand up here and have your fingertips here, and take your right hand, put your palm down here like this. So if you curve your hand just slightly like this and this, bring your two hands together. So I think I need to go on camera to show you what the heck I'm talking about for this one. So hopefully you can see this. I want you to take your hands and curve them together. So when I do this, when I bring my hands together, have I made a converging or diverging lens? So doing that. So if I traced my hands into that shape, would you say I brought light together or pushed it apart? I'm waiting for anything in the chat box. So can you actually, you can see my hands doing my silly little thing, I hope, right? So for a lens that does this, where it curves together like this, we bring it together, we converge. If the lens were to look like this, now trace your hands like this. So I trace my hands off the sweep of that lens. So if you can see that, so the bottom curves up like that. Are my hands coming together or moving apart? Oh, I can't see. I can only shoot. I have my chat box in the wrong spot. I didn't see anybody answering. So sorry if I had that attitude, like, well, why won't you answer? Well, yeah, so if my hands are going like this, diverging, my hands come together. So converge, diverge. So trace your lens with your hands, and that should tell you what these things do. So I'll go back to this mode. So this is a converging lens. My hands have come together. So for this one, light rays come through and they converge. All the rays converge at a spot called the focal point. All the rays pass through. Okay, so hopefully this seems okay then. So reflection and refraction. That's going to be our basic gist here. Okay, so with that in mind, time to start into the rules. I'm going to start with a plain mirror, a flat mirror like you have in your bathroom. And I do apologize because this might be a cultural question, but if you're from California, it's mandatory. Every house must have at least 4 mirrors in every room so we can look at ourselves all the time. So if you're from a different state, maybe you don't have as much mirror access as we do. But I'm just hopefully you know I'm joking, sort of, maybe. But here's this mirror. And again, we're all arrows. So here's this arrow. I can pick any point, bottom, middle, top, any of them, but I'm going to pick the point at top. That's usually what we do. We use the tip. Light can emanate in all different directions off it, but it can go straight out and go up and go down. So for whatever reason, we usually pick predictable angles. We usually pick the one that goes straight out and hits perpendicular. We usually pick a ray that goes to the baseline right here. So the midline of the mirror. So if I do that, light when it hits here, is light going to pass through the mirror or reflect off of a mirror? I forget, light reflect, perfect. So if light hits a mirror and reflects back, where does light finish? Does light really finish on this side or does it really finish on this side? So where does light really finish? It really finishes over here. So this is the real side. This is decided we're going to give positive numbers on the number line to the real side. This is going to be called the virtual side. Light doesn't pass through here. So real image, because the light is actually there, can be projected onto a screen. You can actually hold out a screen and see a real image. A virtual image is like a hologram. You don't actually have the light penetrate. You can see an image, but if you tried to put a screen there, it wouldn't project onto it. So it's like a made-up image in your mind. So the real side is where light really finishes. Virtual side is the opposite side. Okay, so here are our rays. This ray is going to go straight out, reflect straight back. This is going to go down at an angle, going to come out at the same angle. The real side is something you can light up, so to speak. The virtual, yeah. So can you make friends with your identical twin in the mirror, your enantiomer twin, say? Okay, yeah, I forgot. There's a psych-soc section. So for the physics section, no, you cannot be friends with your enantiomeric pair on the other side of the mirror. But in psych-soc, yes. In fact, it's something in DSR-5. I'm so kidding. I'm just totally joking. That's wrong yet entertaining in a way. So yeah. So for physics reasons, we're going to say no. You can't hang out with them. Okay. The thing that my mind does, we can't help it. We're just wired this way. If you've ever seen like a car lot or something at nighttime where they're having a sale, you ever see those big beams of light? They shoot up to the sky. Have you ever seen like that big beam of light? What is your instinct? To follow the light beam out to see which star in the sky it's lighting up, or to trace it back and see where it came from? What is your human nature? Look for the source, see where it came from. We're like friggin' moths. We go gunning for that light source. That's who we are and what we're about. Well, we can't help it. That's just what we do. If we see 2 rays coming out, rather than saying, hey, where do they end up? We inherently, in our mind, trace it back to the origin. So does this dashed line represent a real ray, or is this where I think I perceive that it came from? The dashed line is my mental perception, my imaging to say, well, it must have come from here. So if this ray is coming out like that, it must have come from over here. If this one's going like this, it must come from over here. That point where they intersect, really, cats go to the, somebody just said that like moths go to the source, but cats actually go to the end. Is that true? Oh, you're right. Cats always chase the pointer. Oh, you were so right. They don't chase the reflection. That is genius. Yeah, I forget what commercial it is, but some commercial where they're trapped by a lion and they save the day by putting a laser pointer and the lion chases it. And they don't get eaten. That's my favorite commercial. I don't know what it's for, but if I ever remember, I'm going to buy everything they sell. Okay, so we trace back here. The arrow, the point that we're looking at with the tip of the arrow, so the tip here becomes the image tip over here. So in my mind, I see this. You've seen this tons of times if you've ever looked into a mirror. So if you're right here in the mirror, can you, even though you're facing towards the mirror, can you see the object behind you by looking at the reflection? So even though the object's over here, can you see it behind virtual you over here? Because you trace the rays back. That's just how our image system works. Okay, so this is a virtual image because it's formed on the virtual side. Okay, fair enough. Would it have a positive or negative number to describe its position? So if I said the image is formed at 3 centimeters, or should I say negative 3 centimeters? Negative 3. So by convention, virtual images are negative numbers, real images are positive numbers. It's just convention, just what the rules they say, so I'm going to play by their rules. Okay, a few things I should know about this image. When I look into a plain flat mirror, it's always upright. Virtual, it's always on the other side of the mirror and always the same size. So how many have ever seen mirrors that, like, I don't know, for looking at your face a little more carefully? Let's say you're looking for a blemish, you're trying to do whatever. I think like fancy hotels sometimes have them. First time I ever saw in my life was a fancy hotel. How many know what I'm talking about? Like the vanity mirrors, I think they're called. Yep. So are those flat or are those curved? Those must be curved. Perfect. What about your car mirrors? When you're driving down the road and you look in your car mirror, you agree the mirror inside your car is really tiny, yet you can see the car behind you. Does that mean that that is making a larger or smaller image? If the massive truck behind you can fit on that mirror, do you agree the image creating is much smaller? So that too is a curved mirror. So your cars, they're curved. Your vanity mirrors, they're curved. Your bathroom wall mirrors, or typically wall mirrors in general, are flat. They're plane mirrors. Okay, so got to go through the plane mirrors first, then we'll figure out curved mirrors as we go. Convention again, positive number, it's a real image formed where light really finishes. You can project it on a screen. Virtual image, negative number, it's a hologram. You can't really project it onto a surface, but you swear you can see it. Magnification. This is that rare case where physicists actually use the right letter for the word. And for magnification, it is the height of the image divided by height of the object. You can also, because triangles are symmetric, this angle equals that angle, that's 90, so this angle must equal that one. So the hypotenuse ratio equals the length ratio equals the height ratio. So it's not only the relative height of the image over height of the object, but it's the length of the image over the length of the object. Why is a negative there? So what is the whole purpose of that negative in that relationship right there? It's simply there to undo the negative we put in here. So it sort of undoes that negative, because distance here is a negative number, that's a positive, but we want it to be positive, just for purely for convention. Okay, rules about magnification. If magnification is a positive number, the image is upright, erect. If it's a negative number, it's inverted, upside down. Also, if the magnitude of the number, if the magnification is greater than 1, then the image is larger than the object. It's said to be an enlarged image. If it's equal to 1 and it's the same size, is less than 1, it's a reduced image. So if there was an image that had an I of negative 3.5, and m of positive 0.4, what can you tell me? Is this image right here virtual or real? So is an image virtual or real? Virtual. Why is everybody voting virtual? Because I is negative number, exactly. Is the image upright or inverted? Upright, because it's positive. And is it larger or smaller? It's a virtual image that's 40% as large, so it's smaller, and it's upright. So the conventions, gotta know them. And they hold for all mirrors, all images, mirrors and lenses. So I don't think this is challenging per se, but is it just more stuff to cram into a head that already has too much stuff? So this just another case of just information overload, more stuff to put in there that hopefully doesn't fall out till at least a few minutes after the MCAT ends. Okay, curved mirrors are nice. I want to consider, or plane mirrors are nice. I want to consider a curved mirror. One of the really cool things that maybe you discovered as a kid, if you happen to notice this, but when you look at the back of your spoon, you're right side up. But when you look at the inside of your spoon, are you right side up or upside down? So has anybody ever done this? Looked at your spoon? You need a shiny breakfast spoon, but so how many have done this? Looked at your spoon and you're upside down, but on the back side, you're right side up? Yeah, I seriously want you to do if you have a spoon. Oh, see, that's such a painful comment. No, I don't do that stuff because I have a life, you nerdy physics idiot. I can't believe you said all those words. That's so mean. Okay, I might have embellished and added some of that in there. But so anyway, but yeah, it's just, yeah. I know, I understand it's a joke. I just wanted to take full advantage of it. But yeah, just those silly, nerdy things we do. But if you look at the back side of the spoon, you're right side up, front side of the spoon, you're upside down. Okay, I want to figure out why this is. Do you confirm it, Elton? You are upside down on the inside of the spoon and right side up on the back side? Might be hard to see yourself, but if you put like a pencil or something, something that distinctly you can see that it's pointing up, and put the reflection, you can see upside down and right side up on the two sides. Okay, want to move on from there then. So let's consider the back side of the spoon at first. So I'm going to say the object's going to be on this side. Light's going to hit here and reflect back. So here's my object. Again, my arrow. Again, I'm going to do two rays, the ray that goes straight out. But now when it hits, is it hitting a perpendicular surface or is it no longer perpendicular? So this one will reflect straight back or reflects up at an angle. Yeah, it's no longer perpendicular, so it's going to hit here and go up at an angle. This one's going to come in and come out at the same angle. So let's consider those two rays. So this one goes in, goes out. This one comes here. Are these rays moving apart or coming together? Are they converging or diverging? They're diverging. Perfect. My nature, my instinct, I'm a moth. They diverge. I trace them back and see where they intersect. So this ray happens to always trace back to the F. Just one of those cool phenomena. This one traces back to the, I guess, edge of the universe. Where they intersect represents where they intersected over here. The real rays intersect at the beginning, intersected that image. So what is really cool is the following. This drawing never changes. This ray diagram never changes, so I don't need to draw it again. I simply need to make note of a few things. If this ray always traces back to F, does that mean the intersection always has to be somewhere in here? Would that make sense that if this ray always hits at that point, then the intersection always has to be somewhere to the left of that, but right of the mirror? which means the image can only form in here. Which means, is it going to be larger or smaller than the object every single time? Always smaller. It's also on the virtual side, so it's going to be upright. And that would mean, let me just see. I just want to mention the fact then, from this we have a smaller upright virtual image. Let me write that better. So I think I've seen those letters before. You can SUV. So, I mean, this is so cool. If the test writers give you a diverging mirror that it ends up, they give you a gift. They give you an SUV. I mean, who doesn't want an SUV? So a smaller upright virtual image. Are they coming together? So you're telling me these rays are going there and there? Oh, okay. By the way, was I doing a lens or a mirror? And you just hit on something. This is huge. We got to get this foundation down pat. My hands were coming together on a lens. That hand trick works for the lens. The mirror, for whatever reason, whatever physics person came up with the rules, makes everything different. So here's what you have to do for this. Here's my mirror here. That's a terrible drawing. Let me do it in green. Is this side more like a cave? So if this was something like this, would this be the cave side? So this is the concave mirror. This over here is the convex mirror. It vexes me because it just spreads everything out, whereas here I can hide in the cave. Mirrors and lenses do the exact same thing. So a convex mirror is diverging, whereas a convex lens is converging. So which is a more important word when you're solving questions? Concave and convex, or diverging and converging? Diverging and converging, exactly. Everything revolves around that. So the very first question, the absolute first question you always have to ask, is it converging or diverging? Yep. So exactly. The way light reflects, if it's diverging mirror or converging mirror. Hence there's a name for it. So this is a convex mirror, also known as diverging mirror, because it causes the rays to diverge. But what's really cool, if I know that, if I have a diverging mirror, I always get an SUV. I always get a smaller upright virtual image. Does that make my life easier? If I know the image has to form here, I know always it's smaller, I always know it's upright, and I always know it's virtual. And not only that, it's between 0 and negative f. My life just got super easy. So on the MCAT, if there's a question, blah, 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 diverging mirror, blah, 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 diverging lens, if you see the word diverging, you should stop, take a brief moment to say, thank you, test writers. Because did the test writer just give you a gift? Did they just give you a free brand new SUV, smaller upright virtual image? Yep. Whether it's a lens or a mirror, diverging always gives me an SUV. And that SUV always forms between 0 and negative f, which means that's the easiest question you can possibly get. It's like a gift. It's a freebie. Oh, mine is so blown. But this is the beautiful thing about studying for the MCAT is in real physics, you had to solve everything. But in MCAT physics, can you see patterns and start taking shortcuts like this? So it works out well. Okay, one thing I want to point out, in the previous slide, I used DO for image or object and DI for image position, so O and I. Now all of a sudden I'm using S and S prime. Which is the correct designation? S and S prime, D sub O, D sub I, O and I, P and Q? Or is this one of those damn sections where they have all of them? Is this annoying chapter where you can write your equations multiple ways? So if I'm doing my job right, should I do the way I like, or should I try to do it all the different letters? So how many learned 1 over O plus 1 over I. 1 over object position plus 1 over image position equals 1 over the focal length. So did anybody learn O for object, I for image? 1, okay? Did anybody learn S, S prime? S for object, S prime for image. Okay, so I'll take that as a 1. Okay, so I got 2 response, so 2 and 2 so far. And this is the weird one of all for me, but how many learned P and Q? So that is because, does the P when I draw it this way look like the reflection of the Q? Are they reflections of one another? So the object and its reflection, that's supposedly where P and Q came from. But how many people besides me are completely annoyed that you could see it one of 3 ways? Object and image, P and Q, S and S prime. It is the exact same equation, which means, is this one of those things that's going to be just annoying on the MCAT? Because they may not write it the way you're used to seeing it. So apologies in advance, but the homework, you'll have to have S and S prime, O and I, and P and Q, and they are all the same thing. But I'm doing it that way to make sure you're exposed to everything. So on test A, if they draw it a different way than you're used to, it's not a freak out moment when there shouldn't be one. Okay, so I'm going to clear everything here and say then, we have a gift. We have an SUV complement to that. SUV is always formed between 0 and negative F. This is a negative F because it's on the negative side. So I want you to hang on to that thought. We're going to keep a big picture of everything. So I'm going to start making that. But there's 3 things that are just automatics, and I want you to just literally commit to memory. Diverging mirrors and diverging lenses. A single diverging mirror, a single diverging lens, like this single diverging mirror, always gives you an SUV, smaller upright virtual image. That smaller upright virtual image, that SUV, is always formed between 0 and negative F. And if it's just a single mirror or a single lens, images can be one of 2 types, UV or IR. Just like light that we memorized before. Upright always goes with virtual, inverted always goes with real, if it's a single mirror, a single lens. So one little side note, do we ever have devices that have multiple lenses, like a microscope or a telescope? Those work in a way where it's basically 2 independently operating devices, but the image of the first lens or mirror becomes the object of the second one. So the reason I'm emphasizing that this is for one mirror or one lens, because let's say I have 2 consecutive IR images. So one gets inverted in real, and then it goes through another lens and gets inverted again. Can it be inverted and then inverted back up? Can it be reversed, go upside down and back to right side up if you have 2 lenses? Yep, that's why a lot of our optical devices, binoculars, telescopes, microscopes, they have 1 lens or 2 lenses. 2 lenses, perfect, so that it can flip it back the right way. So if you go upright, upright, that's fine. It's going to be upright. If you invert, invert, it's going to go back to upright. But for a single lens, images are UV or IR. Okay, summary page. I don't want you screenshotting yet until the very, very end, but I'm going to make a summary page where it's going to be diverging and converging, mirror, lens, mirror, and lens. So I'm just going to work on this quadrant for now. A convex mirror. Convex mirror, meaning it is shaped like this. Rays come in, they reflect out, rays reflect out, reflect out. We trace it back to that origin. This is known as a focal point. Is a focal point on the real side or the virtual side? Focal point is on the virtual side. F is a negative number. That's why I have it in bold and red. and always, 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 always forms an SUV between 0 and negative f. Freebie. So if you get a diverging system, a diverging mirror, or a diverging lens like we'll have here soon, what's the first thing you say to the test writers? Thank you, test writer. Write them a thank you card. Oh, I love you. That's a strong one. I love you, test writer. Yeah, if you say it out loud, that will really go over well in the room. I'm curious what would happen if you declared your love for them out loud and audibly. Only one way to find out. Okay, I'm going to go after this quadrant now, and or, I'm sorry, this quadrant for the other mirror. Then I'll go these quadrants after that. So we'll revisit this. So this page is going to get filled in as we go. Okay, and the one at the end is one that I actually want you to screenshot and memorize everything on it when we finally get there. A concave mirror. So now if I'm on the cave side, now here, this looks like a cave. So we have this. It ends up, this one, for everything you said, thank you for diverging one, was converging. You're going to change, it's still going to end in U. And in fact, the first word is still going to probably end in K, like thank, but it won't be THAN in front. It'll be 3 letters, and it's one that probably you've heard on the freeway. So thank you, test writers, or dang you, test writers, because this one ends up being significantly more challenging. We're going to come up with a shortcut, but it's going to take some work. Okay, I want to go back to that equation that we put up there. I'm going to do 1 over focal length, 1 over object position, plus 1 over image position. So I'm choosing O and I for now. Again, P and Q, S and S prime, whatever you want to do. There's a relationship here, so I need to be a little more thorough. F is where all the light reflects, passes through. It's a focal length. R is the radius of curvature, meaning if I took this lens and completed the sphere, completed the circle, it'd be the center. How does R relate to F? That geometry there becomes really critical. So this becomes key. R equals to F, or if you want, F equals R over 2. How many have learned that? How many have learned that this is halfway? F is halfway between R and the mirror. So this is F, this is a distance of 2F. Is that something you recall? Because that becomes kind of helpful here. Okay, a way to help me out with some math here. Is this a true mathematical equation? Is that mathematically true? 1/4 plus 1/4 equals 1/2. Math works out, perfect. So if this number is double, then 1 over double that number plus 1 double that number equals the same original number. So what if that was 2, oh, sorry, that was a bad 2, and that was 2F. So what if that's my F? So what if this is 2 times F, 4, and 2 times F, 4? Would that mathematically work out? 1 over 2F plus 1 over 2F, you agree, common denominators, so just add them across. 1 plus 1 is 2. 2 over 2F, 2's would cancel. Is this mathematically true, just like this was mathematically true? I mean, how many are okay with the math? How many are on board? 1/2 does equal 1/4 plus 1/4. So 1 over F does in fact equal 1 over 2F plus 1 over 2F. Okay, what if this number was a tiny bit bigger than 4? Would it make sense that one have to be a little bit lower than 4 to make it work out? If one denominator gets a little bit bigger, the only way to keep the equality would make the other denominator a little bit smaller. So same thing here. If this gets a little bit bigger, this one is a little bit smaller, which tells us something. Again, this is the object, this is the image. So if the distance of the object gets a little bit bigger, the distance of the image must get a little bit smaller. If the distance of the object gets a little bit closer, the distance of the image has to get further away. How many are okay with that math, that concept? If one denominator goes up, the other one must go down, which means if one gets bigger, one gets smaller, they go in opposite directions. That's going to be really helpful to me. So I'm going to take advantage of this equation to avoid using ray diagrams and math in the future. So I'm clearing in 3, 2, 1. Gosh, Sorry, this is the second time I prematurely bumped it. R equals 2F. F equals R over 2. I'll keep that up there. So real side, virtual side. I'm going to put my arrow on this side. It's going to hit the mirror and reflect back. Here's my equation, 1 over I plus 1 over O. And again, totally up to you. If you want to make that P and Q, S and S prime, whatever you're comfortable with, put it in that sequence. If the object is at the R, and again, R equals 2F, then plugging in, it'd be 1 over 2F plus 1 over 2F, because that's one we just figured out mathematically. So if the object is at F, so 2F, the object's at the R, 2F, image must also form at 2F. So it ends up, without doing a ray diagram, I already knew this. From this equation, I know that the object's at the R, the image forms at the R. So how many are okay with the math of that? One of them is 2F, the other one must be 2F mathematically. So if your object is at R, your image is also at R. It's on the real side, so it's an IR or UR. It's an upright or inverted real image. It is inverted. Ray goes in, comes down here, so object is here and inverted. So I always get either a UV, upright virtual, or IR, inverted real image. Okay, what's going to happen if I move the object a little bit further out? So if I make this denominator a little bit bigger, this has to be a little bit smaller. So I'm going to click 3, 2, 1. So what if the object's beyond the R? Now it's a little bit further away. So it's a little bigger than 2F. So where's the image going to form? Should the image form here, beyond the R? Should it still be at the R, or should it be inside of R? So if the object moves a little bit further away from R, the image should form inside of R. Perfect. So if this number is a little bigger than 2F, this has to be a little bit smaller than 2F, you got it, you nailed it. So my object's beyond the R, my image ends up inside of R. Notice I haven't drawn a single ray diagram yet because I don't draw very good straight lines, and I probably don't have time to draw too many ray diagrams on the MCAT. I'm going to still do ray diagrams because I'm still supposed to know them. So this ray is going to come out here, reflect, and pass through the focal length. This one's going to go to the midline and go out here. So you can do any two rays, and they should all intersect at the same point. So I could do one here and here. I could do one here, and it reflects back. All of them should go to that same point. But we pick the one that goes horizontal, and we pick the one that goes to the midline. Horizontal should always reflect through the focal point for a ray diagram. But the point being is, if I know this is out here, I can guesstimate where that one is. So let's take the same image, and now let's say it's inside of R. So if the object is here, where does the image form? What's your prediction? Inside, at, or beyond? Left of R. Perfect. Nailed it. All over it. So, uh-oh, I'm getting Bluetoothed again. There we go. So 1 over 2F. So my image is going to form beyond the R. Ray diagram is going to do its thing. Perfect. I'm feeling pretty good. So let me summarize. If the object's beyond the R, image is formed between R and F. Object at the R, image at the R. Object between R and F, image forms beyond the R. So a couple other questions asked. What if it's at the F? What the F? Well, mathematically, if this equals F, so let me erase it first. If that equals F, we'd agree 1 over F equals 1 over F. Does that whole thing here have to be equal to 0? So let me get rid of my circles and make note that 1 over F, 1 over F. So that must be 1 over, if this equals 0, 1 over infinity. What does that mean? Image forms at infinity? Means it never forms. So if I draw the ray diagram, it's going to come out here, it goes this way. The rays are parallel, they never intersect. Trace them back, they still won't intersect. Meaning, like you said, if you're at the focal length, you get no image. So just I don't know. I mean, sorry to tap into popular culture, but how many? I don't think it was very successful. But how many read the vampire series? I forget what it was, the Cullens or whatever it was. Book 5, the one where they talked all about the physics and biology involved and how vampires automatically curve every mirror and put themselves at the focal point. That's why you can never see them. And also why, for instance, different vampires feed on different types of blood, like O, A, B, A, and so forth. That's why certain continents have different popular blood types. How many are believing this at all? The crazy thing, that last notion, actually, when you, it's a lie, but it actually has some merit to it. If there is some predator that feeds on one blood type over another. But iconic, oh, hate to disagree. Harry Potter was iconic. That's a well-written story of history and good prevails over evil. Twilight was basically some 108-year-old guy hits on a high school kid and everybody's cool with it. That just, as a parent, I'm a little bit not into it. So, anyway, hopefully this thing's okay. No image. And then finally, this one, I apologize, this could be perceived as inappropriate, but it'll still work. If you go far enough into the cave, weird things happen when you cross that focal point. The image, if this number is less than f, so for instance, if 1 over this, 1 over this, so let's say this is 3 and this is 2, you agree this other thing must be a negative number. The only way that can be equal is if that's negative. What happens if the image is a negative number? That means it's on the real side or a virtual side. Virtual side. So it forms over here. So it's kind of cool. You end up getting, you had IR, inverted real images, completely until you got to here. Once you went inside here, now all of a sudden, the image forms on the other side. It is larger. It is upright. It is virtual. So this image, this is a lovely image. If you go inside the focal length, you get a lovely image. So I'm going to tell you this part of the cave, if you go far enough into the cave, beyond the focal length, get really close to the wall, way in the cave, you're in what's going to be referred to now as the love zone. What happens in the love zone? If you're from here to here, if you're in the love zone, you get lovely images. So, big picture. I want to take everything we just did. I don't want to do any math quite yet. We'll do math in a second. And I want to summarize. So 2 summaries. One, I will do a visual. The next one, I want to do just a summary visual. So I'm hopeful that, okay, so here we have the object. If the object is beyond the R, where does the image form? So if the object is way out here beyond the R, where does the image form? Between R and F. Perfect. Exactly. Inside of R, so between R and F. As my object moves in, I move it all the way to R, what happens to the image? So if the object moves in, the image moves out. Perfect. So they meet at the R. Okay. Then what happens? Well, if I keep on moving the object in, image keeps on going out. Until eventually, if I move it in far enough, what happens when it meets, gets all the way to the F? It's the LA nightmare. No image. No love yet. This is the no image. When you go beyond that, then what do you get? So now what's true, Michaela? Once you're inside of F, where are you located? Now it's a lovely spot to be. This is a really lovely part of the cave. You're in the love zone where you get love images, larger upright. You can make friends with the mirror. Oh, Elton, this is getting dangerous. So, yep, once again, we're back to the psych-soc part. Okay, big picture. I believe it is worth your time to screenshot this and just commit it to memory. It's in the handout, by the way. And if anybody wouldn't mind uploading the handout to the chat box, I think Anybody who came in late, this is a really useful handout for today's lecture. So if the image is beyond the R, where does the image, if the object's beyond the R, excuse me, where does the image form? Oh, thank you, Michaela. I think that's worth 17 karma points. It was worth a lot because it's a good one. Thank you so much. Thank you, Stephanie. You guys do take care of each other. Oh, I'm thanking Stephanie. She's long gone. Am I safe in assuming that people dwindle off because they're spent from the first lecture and they're just going to watch this on video later anyway? Okay. So I'm kind of bummed because that last 20 minutes that disappeared, but you edited it perfectly so they didn't notice it with all the answers to the MCAT, they missed that 20 minutes we just did. It's been removed. So. Okay, so the object beyond the R, image forms between R and F. Perfect. If it's at the R, image forms at R. If it's between R and F, image forms beyond the R. If it's at the F, what the F? Where's my image? And if you're inside of F, you're in the love zone. You get a larger upright virtual image. So probably a good idea to also make note then. If it's between R and F, it's smaller. Same, larger, larger. It is inverted, 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 and upright. I meant my palette, so I apologize. But it's hopefully that works out. But this summary, again in the handout, I implore you, just work from that handout when you answer questions, and you will start getting it conceptually. It'll work out beautifully. Okay, so clicking 3, 2, 1. So now we're going to fill in here. Once we fill in here, we are essentially done because lenses end up being an easy follow-up to mirrors. So light comes in, reflects inward, comes in here, reflects inward. They're converging rays. They all meet at the focal point. F is on the real side, so it's a positive number. And we do this list. Object beyond the R, image forms between R and F. If it's at the R, image at the R. Between R and F, the image is beyond the R. At the F, no image. Inside of F, love zone. Love image, larger upright virtual image on the other side. It ends up, is this also going to be true for the diverging lens? It's going to go here, yes. Is this also going to be true for the converging lens? Yes. This part and this part are going to stay the same. So quadrant here, here, and here. Diverging rules, converging rules. Yep, sort of. Michaela, I'll totally agree. This is always an SUV, always. This one is both on the real side, on the inverted real side, but also can form on the opposite side. So for converging is kind of screwy. Could be on one side or the other. So this one flips. This one is always an SUV though. Yep, they love that. So behind the mirror, always, in front or behind. Okay, so lenses are going to be just like mirrors. So math is going to be the same. So where does an image form for an object 40 centimeters from a concave mirror? The first thing, the very first thing I need to do on every single question is decide converging or diverging. So if you make a cave, you make things come together, or do you make things move apart? So concave mirror is converging or diverging? Converging, perfect. So that's a converging mirror. So do I say thank you, test writer, or dang you, test writer? Dang you, test writer. But that's okay. I know what I'm going to do now. I know that if the focal length is 15, then the R is 30, and the image is at 40. So is that at the R, beyond the R, or inside of R? The object is beyond, so where should the image form? between R and F. So I know it's going to be somewhere between 30 and 15. If I'm lucky, only one answer choice fits in that region, and I'm good to go. I know it's converging, so it's going to be real. It's going to be an inverted real, an IR image between 15 and 30. That probably is going to be enough. That's my entire diagram, my entire drawing. To be mathematically sound, I'm going to rewrite this equation this way. So let me just do the math where this came from. What I did is I did 1 over I equals 1 over F minus 1 over O. I subtracted that from each side. I then multiplied this by O and O, multiplied this by F and F to get a common denominator of O times F. So that made it O minus F over O times F. That's 1 over I, so I flip it around for I, product over difference. So how many are okay that this equation is a real legitimate equation? Perfect, okay? So plugging in 40, 15, and 25. So I always want to do the subtraction first, it's easiest. 40 minus 15 is 25. 40 and 5 cancel out a 5, so 8 over 5. 5 and 15 cancel out 3 and a 1. 8 times 3, 24. If you can get it visually, pick an answer fast. If you can't, is the calculation actually pretty easy? Could I both visually get it and calculation get it very fast? It's actually a pretty great system. So let me throw one more. So clearing my math here, clearing in 3, 2, 1, clear. Convex mirror. Convex mirror is converging or diverging? I don't know. And good. So everybody's seen Brooke's question. Will you have more than one answer that fits between R and F? I have a survey of only one real question I ever did in my lifetime, taking the MCAT 3 times, and only once did I render that. And there was only one answer that fit within that range. So based on my survey of one question over my life, I'd say 100% chance is true. Unfortunately, I guess that's not the best logic, but it definitely worked out one time for me. And if it doesn't, you're going to make an educated guess. How do I remember that? Because I looked for it. There are certain things I specifically look for. So yeah, that wasn't a random, that was a, I wonder if this trick works or that trick works. And because your question was my question. We'll actually do that. I always wonder what kind of answers they give. But in general, how many notice their math answers are very forgiving? You can do some crazy bad approximations and still come up with the best answer. So they're pretty good about not making it a math test, a calculation test. Okay, so for converging, I'm sorry, concave is converging, convex is diverging. What do you say? If they give you a diverging question, what's the first thing you say? Thank you, test writer, because they gave you a gift. What did they give you? They gave you an SUV. So I know that this is 12, that's minus 12. So image has between 0 and minus 12. If there's only one answer in that range, you win. Math-wise, math is a little bit tricky. For a diverging mirror, do I use a positive or negative number for F? Have to plug in a negative number. So it's 30 times negative 12 over 30 minus 12. So 30 times minus 12 is minus 4 or 360. 30 minus a minus is plus, so 42. Let's see, 6 times 7, 6 times 60, so 60 over 7. 7's prime, so I'm stuck. 7 goes into 56 8 times, 63 9 times, so it's 8 point something. Around negative 8.6. Negative 8.6 fits in the range. We're set. So let's see how you do. We're going to give you a couple of questions starting in 3, 2, 1. See you in about 40 seconds. Okay, so for this one, converging, so thank you or dang you? Dang you, test writers. So for this one, F is 10, so R is 20, object is 25. So would you agree the object is beyond the R? So if the object's beyond the R, where does the image form? Between R and F. So I know it's got to be somewhere between 10 and 20. Gets rid of two choices, but dang it, give you a bit harder one. So I can do it one of two ways. I can still do it intuitively. Relative to infinity, is 25 closer to 20 or closer to infinity? 25 is relatively close to 20 as opposed to infinity, which means they're going to meet at 20, so it's close to 20, so the image must be close to 20. So if the object's a little closer to 20, relatively speaking, then image a little bit closer to 20, relatively speaking. Meaning, what's a better answer, 12 or 16.7? $16.7. Perfect. How many just don't feel comfortable in my decision between B and C? How many want a little math? Because I kind of believe you, but that's a little bit sketch. So let's do a little bit of math. Mathematically, O times F over O minus F, 25 times 10 over 25 minus 10, 25 times 10 over 15, cancel out a 5, you get 5 over 3. Uh-oh, Bluetooth. Getting Bluetoothed again. I know it'll kick in a moment. Okay, so there we go. So 5 over 3, 50 times 10 is, or 5 times 10 is 50. 50 over 3, how many degree 50 over 3 is 16.7? Can you do the picture and the math and still have time left over in a minute per question? Yep, you can do these incredibly quickly if you get systematic. For this one, tell me the first thing you're going to say. Why thank you? Thank you, test writer, because diverging. What do you know about diverging? SUV, form between 0 and negative F. So if F is 8, then negative 8 over there. Image is going to form between 0 and negative 8. How many answers fit in the 0 to negative 8 range? Just one. You're done. Thank you, test writer. They made this so easy for us, because is this question far easier in multiple choice format than it is in regular format? Way, way, way easier. Okay, mathematically, I still want to double check, even though I don't need to. Have to keep in mind it's a negative. So 12 times a minus 8 over 12 minus a minus 8. 12 times 8 is 96. 12 minus a minus 8 is 12 plus 8. That's 20. So negative 96 over 20, negative 48 over 10, negative 4.8. How many agree the math was actually kind of distracting? The math was unnecessary. But want to make sure I do it, and have to make sure I always put a negative for this. One more question. 40 seconds. Talk in a second. Okay, so for this one, to get a inverted reduced image, how can that happen? Converging or diverging, first off? Inverted must be converging. Perfect. Okay, so that's going to get us partway there. The second thing is, which system is going to give you a reduced image? Object beyond the R or object inside of R? Smaller, larger. Okay, so how many agree this is the one I need? So would this work out? This was 10, 20, and 30, like choice A, that's looking good. Or in choice C, if this was 20, 40, making that 30, choice C would be bad. How many are actually getting this? How many realize that you can get these questions pretty dang quickly because it's multiple choice? And just to let you in a little secret, was this a class taught on optics, or was this a class taught on optics in a multiple choice world? It is the second one. No pride, no issues admitting the fact that we are learning how to take a multiple choice test on lenses and mirrors. We're not actually learning lenses and mirrors. We are. I mean, we're focusing more on the multiple choice nature of it. Yes, everything reduced image means smaller. So they'd use different words along the way, but reduced means smaller, inverted means upside down. Yeah, it's unique, yet it's exactly what this test is about. Oh, you're welcome. Okay, so on to the wonderful world of lenses. It took us about 40 minutes or so to go through mirrors. Oh, actually, let me do the math real quick, sorry, just to make sure we get this. 30 times 10 over 30 minus 10, 30 times 10 over 20, factor out a 10, 3 over 2, factor out a 5, or factor out a 2, I should say, and get a 5. 3 times 5, 15. Math, negative 15 over 30. It's going to be negative 1/2. Inverted, because it's negative, half means it's reduced. Yeah. And how many read what Michaela just said? Typically, they're freestanding questions, or it's an obscure question added to something on a lens or a mirror. So I know they had a really weird passage in I don't know how many years back, but it was on a device that focused a laser beam at a certain point. So it was kind of like laser, not surgery, but laser targeting. And so you had to know, because the image, like it's focusing that point. So you had to know where the focus was relative to the lens radius of curvature. And that was a passage, but they still had these questions tossed in. Other questions? If you think about how your eye works, so I'm going to tell you something, you tell me if this is true or false. When you are looking at something far away and then suddenly look at something close, your lens has to recurve its shape, has to resize. When you go from looking far away to near to far to near, your lens has to sit there and change its curvature to adjust. Or does your retina move back and actually go out of the back of your skull for a while and then come back to the normal spot and then go back out? So does your retina move a good like 3 feet outside of your head? Or does the retina stay exactly where it is, and does the lens change its shape? How does our eye work? The lens changes its curvature. Meaning, if I go back to this equation, 1 over f equals 1 over o plus 1 over I. What is the fixed variable when I'm talking about my eye? What is the thing that does not change? your retina. Your retina does not move. Your retina is always a certain distance from the center of your lens. What you're looking at can change. You can look at something far away or nearby, and the curvature of your lens has to change. And so if somebody gets older, the fluidity of their lens gets lost, the ciliary muscles weaken, so they can't curve their lens as much. So this becomes an issue. So what actually happens to people when they get older? They become nearsighted or farsighted? The disorder is known as presbyopia. They become farsighted. They cannot curve their lens enough to see something really near. So the object is too close. If this denominator gets too small, so as this number gets smaller, this overall value gets bigger. So this gets bigger. So that number must get bigger, meaning F must get smaller. You can't curve it as much. Yep, so they need glasses that can take a near object and make a faraway image so I can see it. So they lose the ability to make this F smaller. They get locked into, maybe it's like 0.25. They can't change it. But to answer your question, what can they ask? Usually it's laser devices or targeting light, a freestanding question on eyes correction, and occasionally they might give you an actual passage on a couple lenses in a machine, like a telescope, microscope, or how your eye works. But yeah, usually these are freestanding. By and large, they're probably more freestanding than anything else. Okay. Lens. Again, bring your hands together or move them apart. So if you traced your hands, would they be moving apart or coming together for this? Oh, reading glasses depends on whose glass you're talking about. For an older person like me, I would need to take a nearby image and blow it up, magnify it, make it far away. So I need to make a nearby image or nearby object, make a faraway image, make it larger. So it all depends on which eyes you're talking about. Okay, so this one, my hands move apart, my hands diverge, diverging lens. What do you know? Without doing anything else, tell me what you automatically know when I say diverging. SUV, small upright virtual image. The difference is, this is where it gets screwy. Convex and concave change. We name it for this one surface. First surface you hit looks like a cave. So whereas a concave mirror was converging, a concave lens is diverging. And number two, light passes through a lens. Because light passes through a lens, the real side, light really finishes over here. So the virtual is here. So for a lens compared to a mirror, concave and convex change what they're aligned with. And the virtual side and real side flip. So for a lens, the real side is on the opposite of the object. So always ask yourself, where does light really finish? Where does light really end up? It ends up on the really side. So light is really over on the really side. Real side is where light finishes. So for this one, the rays, when they go through, are diverging, trace it back, intersect there. Lo and behold, is it the same story? Is it an SUV formed between negative F and the lens? Perfect. We use this for the correction of nearsightedness. So if I can see things near, would it be good to take a faraway object I can't focus on and create a nearby image which I can now see? So if any of you are nearsighted and you wear glasses, in fact, if you're wearing glasses now, are your glasses thicker on the edge or thicker in the middle? And asking you to volunteer this information if you don't mind, but yeah, thicker on the edge, thin in the middle, because you need a diverging lens to take a faraway object and make a near image so your eyes can focus on the near image. Okay, so I want to just mention that. So they take a faraway object, make a near image so I can see it better. Here's how the eye works. So corrective lenses for something known as myopia, nearsightedness. The problem is the normal eye works this way. Light goes through, it hits a lens, it focuses on the retina, perfect, we're all good. But notice this lens is a little excessively curved on the outside. The bigger the curve, the more it's like a circle, the more it's going to bend light. So that lens is a little bit abnormally formed, and the rays form prematurely. So in order to focus at the retina instead of before the retina, do I want to spread the rays out or bring them together? Which is going to help? If I bring them together, they're going to hit even sooner. Actually, I need to spread them out. I need to do this. I need to have a device like this where the rays go in and they spread them out. So now they come together and meet at the retina. So does this progressive picture make sense? The standard eye, the slightly abnormally curved eye, and the corrective lens to help it. The lens does not need to be attached to the eye. It can be mounted on a frame. It can be attached to the eye like the contact lens. I don't know, define what astigmatism is. Yeah, so I'm going to go with not exactly. This is just basically a lens focusing issue. There's certain disorders that are point defects. So I'm gonna dodge that one and just say no. Myopia is not exactly astigmatism, but in myopia is one they like to ask about. But there are certain like defects in lenses of one specific point. And also, did you learn this in psychology? The blind spot, the fact that you're on your retina, there's going to be one spot that you just can't see anything because that's where the optic nerve connects and there's no active receptors. How many learned that at some point? Yeah, so that's a point imaging phenomenon, I'll say. So I'm going to ignore all that. I'm going to ignore that psych aspect and just assume everything's perfect, that the retina picks up uniformly everywhere. Oh, I know. You can do experiment by putting a finger in front of you and just totally mess with yourself. I think it's kind of cool. Okay, we're going to fill in this spot right here. The diverging mirror at a negative F. The diverging lens, also negative F. Diverging mirror, the light stays on the real side. Mirror, here it passes to the real side because it's a lens. They switch. Notice real and virtual opposite sides for a lens and a mirror. Notice convex and concave. The words change for diverging. Just have no diverging. The things in red stay the same. Always an SUV, always between or negative F. So guess what's going to happen here? Same story. So for the lens, my hands come together. So this is a converging lens. I'm going to cut to the chase and tell you this. If the object's beyond the R, image forms between R and F. If I move it in, object at the R, image at the R. Move it in further. If the object's between R and F, image forms beyond the R. If you get to the F, what the F? Image is gone. And if I move inside here, I located the love zone. The love zone is very helpful if you happen to suffer from a disorder known as presbyopia or hyperopia. They're two different disorders, but same end result. And that is the following. If I cannot see an object because it's too close, can this lens, as long as I'm inside the focal length, create a larger upright virtual image far away? So do an impersonation of your parents trying to read a menu at a restaurant or a small print on a piece of paper. Do they get it really close to their eyes, or do they stretch their hand way out and tilt their head back? Feel free to be as mean as you want. Okay, if they get it really close, it's an illumination issue. It isn't bright enough. Oh no, were you pushing the menu way out? So if it's up close, it's lumens. You're starting to lose some of your rods. But if you've never seen them stretch their arm out to see something, to focus on something? Yeah. So if it's like not such fine print, they just have to see something, they generally tilt it back. So they can't see up close, so they have to make an image. That means their focal length is limited by about arm's length. The focal length on their glasses is way out here. So their lens, if you look at somebody who's farsighted, their lenses, how many ever looked at them and you swear it looks like a flat piece of glass? It's really hard to see the curvature because their radius of curvature is so massive that little segment you take doesn't look very curved. How many have ever noticed that? That like your grandparents' reading glasses probably don't look like they have any curvature at all. Yeah, barely enough because you have to have a big curvature so that F is big so that everything you need fits within that. Okay. The disorders are hyperopia, that's early onset, rare, but it does happen. The most common cause of that one is the eyeball is a little too short. So again, here's my normal eye. If the eye is a little bit shorter, so notice this distance here is a little too short, abnormally short eye. So you need to diverge or converge these rays to make it strike at the retina. You need to bring them together. You need to converge them. So your lens has to be a converging lens. Lens converges the rays ever so slightly, and then they meet here. So which one can you have laser surgery for? The one where your eye is too short, hyperopia, or where you have a misshapen lens, myopia? So LASIK changes the shape of your eye or the shape of your lens? Changes the shape of your lens. You shave off the excess lens. One of two ways: you can take a slice in the middle, put it back on. Lens surface stays smooth so you can see immediately, but you have complications eventually of the missing material when it fills in, will have a halo. Or you can sit there and abrasively cut the lens off, polish it up, it'll heal itself, but it usually takes about a month, but you don't have halos. But lens surgery is for myopia. Hyperopia, you can't really do much about this. Can't really rebuild the eye. So presbyopia, that's adult onset. You lose the ciliary muscles, you lose the fluidity in your lens, so it can't curve to a smaller radius. And then hyperopia, abnormal eye shape. Summary, same thing we did before. Object beyond the R, image forms between R and F. At the R, forms at the R. Between R and F, forms beyond the R. At the F, what the F? Inside of F, you're in the love zone. You get a larger upright virtual image. How many are okay with these tables? The tables make sense. Everything fits. The difference is the images are now on the opposite side with the lens, the same side for a mirror. I mean, sorry, yeah, same side for a mirror. And then summary. So I'm going to click real quick. We're going to be complete. All I need is a picture of this. And we are good. Real side over here because light passed through, virtual side on this side, F is a positive number. If you know this, if you can translate the terminology here, there is nothing you will not be able to do on that test. Add in the thin lens equation and you're set. So how many feel pretty good about this? How many actually feel reasonably confident that you have a big enough knowledge base of how to attack a multiple choice test? So 3 more questions and you will earn your passage out of here. So 40 seconds, talk soon. Converging or diverging? Converging, perfect. So knowing that, positional analysis. Dang you, test writer. Object is at the R, beyond the R, inside of R? At the R. So where does the image form? At R, perfect. If it forms at the R, it's bigger, smaller, or the same size? Same size, perfect. So information processing. So mathematically, product over difference. 30 times 15 over 30 is 15. 30 minus 15 is 15. 15's cancel. End up with 30. So object at 30, 30 divided by 30 for magnification. We're set. Okay, for this one, dang you or thank you, test writer? Thank you, test writer. So what do I know automatically? SUV, which means it's a U and a V, so get rid of C and D. And between 0 and negative F, so what's F? F is 20, so it's got to be between 0 and 20. Is there an answer that's between 0 and 20 and upright and virtual? B is the only possible answer. So because it's concave and diverging, I know it's an upright virtual image and has between 0 and 20. That's possible answer. Math-wise, if you want to do that, sorry, it's taking a second to kick in. So 30 minus or times minus 20, 30 minus and minus 20. So negative 6 over 50, negative 60 over 5, negative 12. How many did that in seconds? And got it right? How the heck do people get it wrong? Easy to make a math error. And a lot of people count on math or ray diagrams. You're counting on over like big picture visualization. That's the main thing you're doing. So last question, a nearsighted person. What's true for a nearsighted person? Need a diverging lens, need thick on the outside, thin in the middle. So perfect, so a divergent lens. Is divergent the same thing as diverging? Is convergent the same thing as converging? You mean tell me we can say things multiple ways, being physics? Perfect. So we can. The rays bend too much to begin with. So we need a diverging lens. And then image-wise, again, this is what a corrective lens did. Diverging rays spread them out so they met here. If you don't spread it out here, if you don't spread those rays in this spot, then that means they're going to come together sooner or later if I don't have that correction. Come together sooner. So if I get rid of that lens, they focus too early. This is an exaggerated picture. It's just a little before the lens, but hopefully it seems okay. So how do you feel about this stuff? Somebody said it earlier. It's all about reps. I think, Brooke, you said it? Oh, Brooke has disappeared. Man, we had like 18 and it dwindled down. Was cars just so massively overwhelming today that it just took everybody's, sapped everybody's energy? Yeah, I think that's Patricio's go-to, make you sit and do a bunch of passages. And it's tiring and draining. So anyway, sorry, thanks for hanging out. I realize it's a bit much. So I hope this one is just a nice, like, easy summary. This is one of those things, the sooner you apply it, the better. But if you're totally spent, I get it. But try to jump on this, like, some questions for this one in the next, like, I don't know, day or two. Yeah, I definitely think this is a game-changing lecture. There's like three, the acid base, this one, and electrochemistry, I think, are just three huge ones. And I gotta admit, I'm gonna miss doing them. So I'm gonna pick your guys' brains on what suggestions you were, because it's finally dawning me as I've hit December and this is the end of the ride. I'm already getting pretty sad missing it. Anyway, some secret message, see what it says for you. We do have a month left together, but it's like, I don't know, it's going to be done. And this is the end of the run, just kind of a weird heavy moment. Anyway, I hope this all falls into place, power through. Oh, I do have, I have next week and a few others in office hours. Yeah. I'm just saying it, yeah. I mean, all those things are happening, but I'm looking at, after doing this for like 33 years, I started a company before this one as well. It's like end of MCAT. So on the 33-year scale, 1 month is hardly anything. Whereas in your reckoning of like 60 days to go through the MCAT or 45 days or whatever it is, we're in a different mind frame. So I know, thanks for actually updating the calendar. Oh, I can't take the MCAT anymore. I've exhausted my limits. I actually have to apply. Plus I have to register because I worked at a med school. So because I have test prep, they don't care. But because I worked at a med school and was on the other end of things, and because I beta tested once, I'd have to go through a whole bunch of hoops to do that. I don't think they would. I don't think I would be a candidate to take the test. But old potato. Anyway, okay. I'm going to go ahead and stop the screen share. And oop, that didn't work out well. There we go. And then, did everybody get the handout? Because this is just a really, really useful handout. Oh, you're very welcome. Okay, perfect. All right, then I will see. I had a ton of questions submitted for tomorrow, so tomorrow's going to be a long one. So I'll see you guys tomorrow.